In this video, we're going to look at finding sums using our Taylor series. So we're going to pick some interesting examples. And they're kind of fun. And we'll start off easy. The first example says that we have 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. That factorial ran together. 1 over 4 factorial plus dot, dot, dot. So that's the problem giving to you. And it says to use the table of Taylor series to find the sums. So when you look at the table of Taylor series, what I'm looking for is I have factorials in my denominator, and it looks like I just have 1 in my numerator. So if you look at which ones that is, the factorials happen in several of them. Let me bring the table in so we can talk about it. Okay, so this is a really good table of common Taylor series. You can see that includes the binomial one, which I don't know that all of them do, so it's really good. And the radii of convergence, because they can be accepted, don't have to be proven every time, because they don't change. So we're looking for the ones that have factorials in the denominator. So there's a factorial in the binomial expansion down here. There's a factorial in cosine, there's a factorial in sine, and there's a factorial in e to the x. Now, if you look at the binomial has a lot of stuff happening. The one down here has a lot of stuff happening in the denominator, so let's not go there. The cosine, the denominators are even factorials, and sine, they're odd factorials. So it looks like this e to the x is going to be our winner. So let's compare that to what we have. So could this be 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus dot, dot, dot. And it does. So if you look at the fact that x equals 1 in the numerator of all of those, then we know that we're going to say since x equals 1, then we know that the series equals e to the x, which is 1. So that means this series adds up to be e to the first. Because the series can be represented as a sum of the terms on the right, then we put x in here, and the series equals the sum of the series equals e to the x. So it's not a difficult process if you can figure out but when you can figure out which of the series you're looking at. So let's look at another one. That one was easy, so let's step it up just a notch. How about that? Let's say x to the third plus x to the fourth plus x to the fifth plus x to the sixth plus x to the seventh plus dot, dot, dot. You kind of see that happening here. So again, let's look at our table. Take a minute and think about which one you think that might be. When you look at it, which one would you pick? Yeah, I would pick the top one. It doesn't have any factorials in the denominator. It doesn't have any denominator at all. It's just the top one. So we could say this equals 1 over 1 minus x, but not the way it is because it's missing some terms. But we can't add terms to it. So the best way to think about it is, let's think of that x to the third as a GCF. So if we factor out the x to the third, then we have 1 plus x squared plus x to the third plus dot, dot, dot. Oh, that's looking very nice. Go back to that table. Tell me you have that table handy. So when you go back to that table, we're going to bring down this x to the third, and that series adds to be 1 over 1 minus x. 1 over 1 minus x. So then we're going to put the x to the third on top, and it's x to the third over 1 minus x. And that's the sum of that series. It doesn't get more detailed than that because it has an x in it. It's not just numerical like the last one we did. If you have a number there, then you can come up with a nice numerical answer, but they didn't do that. They gave us x's in this one, so I thought it was important for you to see. My goal is to help you out with what you're supposed to be doing. So this is the answer right here. And let's look at another one. So this one says 2 over 3 minus 2 to the third over 3 to the third times 3. My thirds are a little hard to read. Plus 2 to the fifth over 3 to the fifth times 5. minus 2 to the 7th over 3 to the 7th times 7 plus dot, dot, dot. So let's bring that table in again. Yeah, I'm going to provide this table for this part of the problem. Okay, so let's look at what we have going on here. This looks, if we look at the powers, we have powers in the denominator and powers in the numerator. There's a lot going on, a 2 and a 3. So look at the table for a minute. Yeah, pause, take a minute, figure it out, look at it. Let me give you a hint if you have paused and you're like, I still don't know. Notice this 3, 5, 7 here, and that the powers match. So that's going to say 3, 5, 7 here, and the powers match. So let's rewrite this to say 2/3 minus, there is a minus here, so that's a good sign, minus 2/3 to the third times 1 over 3 plus 2/3 to the fifth. I'm going to move the table over a little bit. 2/3 to the fifth times 1 over 5 minus 2/3 to the seventh times 1 over 7 plus dot, dot, dot. Now, you could think of it this way, 2/3 minus 2/3 on the top of a 3, like this, because that the 3 to the third would move to the bottom with the 3 there. This will help you see it more clearly off the table. Over 5 minus 2/3 to the 7th over 7 plus dot, dot, dot. Does it match one of those lines of the table now? Hopefully. So let me pull the table back over. It's inverse tangent. I was looking for the notation in that table, and it was, so it's inverse tangent. But notice if you look at them, the x has that power in the numerator. See, it's x to the 7th, x to the 5th. The minuses are in the series written out, and so all you need is the x. So the table says the inverse tangent of x, and in this case, x is 2/3. So we have the inverse tangent of 2/3. Do you see where that came from? Let me say it again. See how these x's are on the top? Right here I have x to the 7th, and here I have x to the 7th. This is x to the 5th and x to the 5th. So you can see how x in that case is 2/3. So our series says the inverse tangent of x. So we're going to go ahead and call it x to the 2/3. Hopefully you see that. And then we pause to think, do we know the inverse tangent of 2/3 right off the bat? It's not a special triangle, so we can leave it as the inverse tangent of 2/3, and that's our answer. So the series that we are given in red at the top, it adds to B, the inverse tangent of 2/3. You could come up with a decimal there. It's not very difficult, but you see how it's easier to come up with that summation by knowing that it equals the inverse tangent of 2/3. So that's why we use our Taylor series to help us find sums. Let's do one more. All right, let's look at this one. It says x to the third minus x to the fifth plus x to the seventh minus x to the ninth plus x to the 11th minus dot, dot, dot. So let's bring in our handy dandy table. So some textbooks have another one that's on their table that's not on this one that I posted here. So let me add it for you. It says 1 over 1 plus x equals the series from n equals 0 to infinity of minus 1 to the n, x to the n, and it has a radius of 1, by the way, but let's not throw that radius on here yet. Let's say that equals, it's an alternating series, 1 minus x plus x squared minus dot, 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 plus negative x to the n, and that n's inside. Let me try that again. Plus negative x to the n plus dot, dot, dot. And it has a radius of 1. So I was going to say, take a minute, look at the table and figure out which one you want to use, but I kind of gave it away. So hopefully you can see which one to use. So let's talk about the fact that, but that starts with the 1 and ours starts with x to the third. So let's factor out an x to the third. And if we factor out an x to the third, we're going to see 1 minus x squared plus x to the fourth And then when we take x to the ninth and divide, we get minus x to the sixth plus x to the eighth minus dot, dot, dot. Close parentheses, squeeze that in there. All right, now that does not look like the form we need it to, because look over here, it's 1 and it's x squared. So can we manipulate this to look more like that? So could this just be x? Could we just call it that's x? And then if we take that and square it, do we get x to the fourth? And then the next one here would be minus x to the third, right? So let's erase that plus because that's incorrect and put a minus here. Minus x squared to the third plus x squared to the fourth minus dot, dot, dot. So do you see how that we're making it look like the pattern for the series? So then when we do that, we have an x to the third out front, and that can be replaced with the form of 1 over 1 plus, and in place of x, we have x squared here. So this gives us x to the third times 1 over 1 plus x squared, which is x to the third over 1 plus x squared. And like I said, if we had a number here, we would be able to come up with what that number is, but that is the sum of that infinite series. We're going to do one more because you really need to see one with a derivative in it. So here we go. All right, so this problem says negative 1 plus 2x minus 3x squared plus 4x to the third minus 5x to the fourth plus dot, dot, dot. So it starts off looking very much like the one we wrote in on the last one. So let's go ahead and make a note here. Let's say note 1 over 1 plus x equals 1 minus x plus x squared minus x to the third plus x to the fourth minus x to the fifth plus dot, dot, dot. Now, we've talked about things, but look at how these compare. First of all, the signs look a little off, but let's come back to that in a minute. Do you see a relationship between this term and this term? I would say that if you take the derivative of the note, you're going to end up with something very similar to the original problem, which is really what we want to do. So what we're going to do is we're going to work off of our note and end up with the original problem. When you're working with derivatives, that's kind of the way you want to go with it. So we're going to take the derivative of this side, and we're just going to say take the derivative of this side, and we're going to say take the derivative of this side. 1 minus x plus x squared minus x to the third plus x to the fourth minus x to the fifth plus dot, dot, dot. All right, so let's talk about the left side. When we take the derivative of 1 over 1 plus x, most students struggle with that in their head. So let's say the derivative of 1 plus x to the minus 1. So it's chain rule. The derivative of something to the negative 1 power is negative 1 times that something to the negative 2. And the derivative of the inside, the derivative of x is 1. So this equals negative 1 over 1 plus x quantity squared. Do you see that to be true? Back it up and think about it. So on the left-hand side, we get negative 1 over 1 plus x quantity squared. And on the right-hand side, we're going to take the derivative of 1 to be 0, the derivative of negative x to be negative 1, the derivative of x squared to be plus 2x, the derivative of x to the third to be minus 3x squared, the derivative of x to the fourth to be positive 4x to the third, and the derivative of negative x to the fifth to be minus 5x to the fourth. And we're going to say plus dot, dot, dot. Now, if you go back, that matches our original problem exactly, doesn't it? Since it matches our original problem exactly, all of this equals this term right here. So we could go back up to the top and say this equals negative 1 over 1 plus x quantity squared. That's our answer. So that series adds to be that. The reason this skill is helpful is because it lets you find very easily, often, the sum of an infinite series. So it's helpful in that regard. It's a great application of it. Have a great day and let me know if you have any questions.